All right, so in this chapter, we are going to talk about fluids. Fluids are substances that can flow, and typically they are uh, gases and liquids. What is the difference between a solid and a fluid? It's probably something you already know. In a solid, the atoms or molecules more or less maintain their fixed positions. They might vibrate about that fixed position, but they mostly maintain their fixed positions. And as a result of that, a solid object maintains its shape. Whereas for a liquid or a gas, the atoms can move very freely past one, they can slide past one another. They don't maintain any fixed positions. So there is no long range orderly arrangement of the atoms or molecules that make up liquids and gases. And therefore, liquids and gases just take the shape of whatever container they're in. The difference between liquids and gases is in the fact that the forces between the molecules of a gas are much weaker than the forces between the molecules of a liquid. And so the gas molecules have a lot more freedom to move around than the liquid molecules. Okay. All right. So the first important concept that we're going to discuss is the concept of pressure. So what is pressure? Suppose just imagine this device right here. This is a pressure measuring device. So first of all, we'll imagine that this device is very, very tiny, right? And it consists of this cylinder with a piston, movable piston, and there is a spring between the piston and the back wall of the device. Now, suppose you push down on this piston, and the force that you're applying is delta F, right? And let's say that the area of the piston is delta A. We have these little deltas next to the F and the A just to indicate that they are very small. This whole device is extremely small. So the pressure that you're applying is defined as delta F divided by delta A. That is the definition of pressure. So if you're applying a force delta F on an area delta A, then the pressure is defined as delta F divided by delta A. The unit of pressure is 1 Pascal, and a Pascal is simply a Newton divided by a square meter. Okay. So you can use this device, our little imaginary device here, to measure the pressure at any point inside a fluid. So just imagine taking this device into this red square, which consists of which is a container that consists of some gas or fluid, and moving it around from point to point. The fluid will exert a force on the piston and push the piston in, and that force can be easily measured with the help of the spring, because you know that the spring constant, if the spring constant is k, then the force exerted by a spring is k times x. So by just seeing how much the spring has compressed, you can measure the force, and then you can divide the force by the area of the piston, and you could get the pressure exerted by the fluid at that point. And so this way you can calculate the pressure at each point inside the fluid, right? So, but this device, I must emphasize, is completely imaginary. We don't have a device like this. Pressure measuring devices work in a different way. But in principle, this would work. And so this gives you an idea of the pressure at different points in a fluid, how you can measure the pressure at different points in a fluid in principle. Okay, now if you have a certain area A, and let's say that the force on this area is the same everywhere. So the force at this point is the same as the force at this point, same as the force at this point. So in that case, you can define the pressure over this entire area as force divided by area, right? So that is if the force is constant over a certain area A. If the force is not constant, so suppose if the force over here is very large, but the force over here for some reason is small, then of course you would have to define the pressure at a point by just taking a tiny little area over here, calculating the force over that tiny area and dividing by that tiny area. That would give you the pressure approximately at that point. If you want to find the pressure exactly at that point, then you would just make the area very, very small surrounding that point and do the same operation. So the pressure at a point is given by this formula. And if the force is uniform over a certain area, then you can just do force divided by that area to get the pressure. Okay. Here's an example of a problem. I'll let you read it. So you have a container that consists of two different fluids, which are separated by a partition. The pressures of the fluids are P1 and P2, and for simplicity, we'll just assume that the pressure is the same everywhere for that fluid. So it's the same, it's P1 over here, everywhere on the left side, and P2 everywhere on the right side. You want to find out the magnitude and the direction of the net force on the partition, right? So if the pressure is the same over a certain area, then we can say that pressure equals force divided by area. So what is the force exerted by the gas on the right side of the partition? So the pressure everywhere on the partition is going to be P2. The area of the partition is A. So the force exerted by the right side, the gas on the right side, is going to be P2 multiplied by A. What is the force exerted by the gas on the left side of the partition? That is going to be P1 multiplied by A, exactly the same reasoning. The pressure everywhere on the left side of the partition is P1, and so you can use force equals pressure times area. So the force is just going to be P1 multiplied by A. And so what is the net force on the partition? The net force will be to the left, and the magnitude of the net force would be P2A minus P1A, or in other words, P2 minus P1A, which can be written as delta P multiplied by A. So the net force is equal to the difference in pressures multiplied by the area. This formula is useful because you often have a situation like this, like you have some kind of a partition and you have two different pressures on both sides, and you want to find out the net force due to the difference in pressure. And so it's just the difference in pressures multiplied by the area of the partition. Okay. Let's try this example. This would be a top hat example in class, so feel free to pause the video and see if you can figure it out. Okay, the solution is, the question is asking which one exerts a greater pressure on the table if the weights of the blocks are the same. The solution is the one that's standing upright. And why is that? Because the force would just be pressure divided by area, right? The force exerted on the table by each block is simply the weight of the block. And since the blocks are identical, the weight of the block the weights are identical. So the pressure on the table is simply going to be the weight of each block divided by the area over which the weight is acting. And so in this case, this quantity is going to be smaller. The area is going to be smaller. So the quantity itself is going to be larger. So I'll just write, this is a higher pressure and this one exerts a lower pressure. Okay, The next thing that we're going to talk about is the pressure at a certain, we're going to find the expression for the pressure at a certain depth in a fluid. All right. Okay, so let's see if we can figure this out. So suppose you have a container filled with some liquid, and let's say that the pressure over here, so this is the height y2. And this is at a height y1. This point is at a height y1. Okay, and let's assume that the pressure at this point is P2, and the pressure over here is P1. We want to find an expression. We want to find an expression which connects P1 and P2 to their heights y1 and y2, right? And obviously we are measuring heights. We're setting y equals 0 over here. You'll find that it doesn't matter where you set y equals 0. I could have set y equals 0 wherever I wanted. Okay, so how do we find the relationship between the two pressures at these 2 points and their respective heights? This is a nice application of what we learned in the last chapter, which is equilibrium. So let's imagine drawing a little cylinder, imaginary cylinder, like this. Okay, such that the 2 points are at the faces of the cylinder. And remember, this is a cylinder made of water, made of the fluid. We'll just take the fluid to be water, but let's just take the fluid to have some density, rho. So it's not necessarily water. Rho is the density of the fluid. All right. So what we're going to do now is we will calculate this relationship. Okay, I'm sorry, I'm getting distracted by these pens and all the pen options. This is the first time I'm using the Notes app. So anyway, all right. So let us consider the equilibrium of our cylinder of water, I should say fluid rather than water to be more general. So this yellow cylinder is just, the fluid is entirely at rest, right? So the main thing here is that our fluid is at rest. So so if we consider this yellow cylinder of water, obviously that's at rest because every part of the fluid is at rest. So this yellow cylinder of water must be in equilibrium, right? What are the forces acting on this cylinder of water? Well, there is, if I draw more things on this diagram, it'll get more complicated or more cluttered. So I'm just going to draw our yellow cylinder separately over here. What are the forces acting on this cylinder? There are 3 forces, and we are only going to consider the forces in the vertical direction, right? So there are 3 forces acting on the cylinder in the vertical direction. One is a force that comes from the pressure of the top surface. And then there is a force which comes from the pressure at the bottom surface. And then there is the weight of the cylinder, mg, acting down, right? So what is the force due to the pressure at the top surface? From the formula that we just learned, the force is just going to be pressure multiplied by area. So the force over here will be P1 multiplied by area. And the force at the bottom surface would be P2 multiplied by area. Now, you might say that how do I know? So the formula pressure multiplied by area is true if the force is uniform over that area. How do I know that, for instance, at the top surface, the pressure is P1 everywhere, not just at that point? So I'm assuming that the pressure is P1 everywhere on the face of the top surface. How do I know that that's the case? Here I'm using a result which I haven't proved, which is that the pressure at a given depth is always the same. So the pressure only depends on depth. At a given depth, the pressure is always the same. So we're assuming that pressure at a given depth is always the same. So that's how I know that it's okay to use pressure multiplied by area for the top face, because the pressure is going to be P1 everywhere on the top face and same at the bottom face. Now let's do equilibrium. So equilibrium means net force equals 0, net torque equals 0. We just need net force equals 0. So if we do net force equals 0, which we can choose a sign convention, upward is positive. So in that case, P2A minus P1A minus mg would be equal to 0, right? Okay, now let's figure out what this mg is going to be. How much mass is there in the cylinder? You know that mass is volume times density. This formula is going to be very important in this chapter. The definition of density. The density is mass divided by volume. So I'm sure you've seen this formula at some point. So we are often going to use mass equals density times volume in this chapter, right? So let's do that now. So P2A minus P1A minus the yellow cylinder is just made up of water. So it's just going to be fluid. So density times the volume of the cylinder multiplied by G. Let's figure out what the volume of the cylinder is going to be. The length of the cylinder is going to be y1 minus y2, right? And the area of the cylinder is A. So the volume is just going to be, okay, let me write this out. P2A minus P1A minus rho multiplied by the volume of the cylinder, which is going to be area times y1 minus y2 times G is equal to 0. So now it looks like we have an equation which connects the pressures and the heights. Does this simplify? Yes. So all we have to do to simplify it is just divide both sides by the area. So if you do that and if you move the last term to the right side, you get this equation P2 minus P1 is equal to rho G y1 minus y2. This is a very important equation. It tells you what is the relationship between pressure and depth, right? Okay, now we were considering, and since we can't see the diagram, what we just did was we got a relationship between 2 points which were at heights y1 and y2. And we connected the pressures at the 2 points. So the pressure over here was P2 and the pressure over here is P1. Okay, now typically we are interested in knowing what is the pressure at a certain depth underneath the surface, right? So our point y1 is usually at the surface of the fluid, right? So let y1 be the be at the surface of the fluid. So our upper point is at the surface of the fluid. So in that case, what is the pressure P1 going to be? Let me just draw the point P1 at the surface while you think about it. So what's the pressure P1 going to be in that case? It's just going to be atmospheric pressure. So if Y1 is at the surface, then P1 is simply the atmospheric pressure. That's another important thing in this course. Any point which is directly in contact with the atmosphere will be at atmospheric pressure. And atmospheric pressure, we're going to talk about that in just a little bit, but it's simply the pressure exerted by the atmosphere. Okay, so P1 would be P atmospheric. And Y2 minus Y1, or Y1 minus Y2 would simply be the depth below the surface, underneath the surface. We're going to call that H. Okay, now P2 minus P atmospheric in that case is equal to rho G H is what we're getting. All right, so you can see from here that the pressure at the point Y2 underneath the surface is going to be greater than the atmospheric pressure by an amount, rho GH. Rho is the density of the fluid. G is the acceleration due to gravity. There's nothing new about that. H is the depth underneath the surface. This is a very, very important formula. Now, atmospheric pressure is something that we are all used to. So we don't know any different. We've always lived with atmospheric pressure, right? So we don't even sense the atmospheric pressure. It's only when the pressure is different from atmospheric that we notice it, right? And that's why it makes sense to define a new term, which is called the gauge pressure. That is just the difference between the pressure and the atmospheric pressure. So I'm going to call the gauge pressure as P. Gauge pressure is simply the pressure over and above atmospheric. I mean, pressure difference between the actual pressure and the atmospheric pressure. And the reason for defining the gauge pressure is because we don't, if the pressure is atmospheric, as far as we are concerned, it's zero, because we don't notice the atmospheric pressure, right? So a pressure is only significant to us if it's different from atmospheric pressure, if it's lower than atmospheric pressure or greater than atmospheric pressure. So it makes sense to define a new pressure as the actual pressure minus the atmospheric pressure, and that is called gauge pressure. And gauge pressure is a good name because that is exactly what a pressure gauge measures. It just measures the gauge pressure. A pressure gauge will show you zero if the pressure is atmospheric, but it will the pressure that it indicates is just the difference between the atmospheric pressure and the actual pressure. Okay, so we're going to call the pressure at P2 minus the atmospheric pressure as P. So P simply represents how much greater is the pressure at depth Y2 over and above the atmospheric. And so that is going to be equal to rho times G times H. And this is our first extremely important formula. Okay. Let's look at an application of this formula. See if you can work this figure out this question. Which of the following has the greater pressure at the bottom? Is it at the bottom of this shallow lake, which has an enormous amount of water, or is it at the bottom of this deep pond, which has a small amount of water? The correct answer is B. The pressure at the bottom of the small deep pond is going to be very much larger. It's going to be larger. Why? Simply because of this formula. P is equal to pressure at a certain depth is equal to rho GH and H is greater. It's 6 meters for the small pond, but only 3 meters for the large lake. Okay. All right, so I have a couple of problems here on this, so you can look at these yourself. Okay. Now let's talk about atmospheric pressure. So first of all, an interesting question, which is not really relevant for this particular chapter, is why do we have an atmosphere? Now, you might, um, if you think about it, an atmosphere is just some gas which seems to be stuck to the surface of our planet, right? The atmosphere goes up for about 100 kilometers above the surface of the planet, um, and it progressively thins out. And so at 100 kilometers, you will hardly detect any atmospheric gas at all. The atmosphere is much thicker as you get closer to the surface of the Earth. In fact, um, 50% of the atmosphere is below about 6 kilometers from the surface. So you can see that it's a lot thicker near the surface, and it gets thinner and thinner and thinner as you go further out. Okay, so the question was, why do we have an atmosphere? Why didn't the atmospheric gases just sort of diffuse away and just go out into space? The correct answer is because of gravity. So we're going to learn in chapter 13 that there is a certain speed, minimum speed that an object must have in order to escape the Earth's gravity, and that's called the escape speed. If you look at the average speeds of the molecules in our atmosphere, it's much less than the escape speed needed to escape the gravity of the Earth. And as a result of that, the Earth has an atmosphere. Um, the moon has a much weaker gravity, and so the moon doesn't have any atmosphere because its gravity is not strong enough to hold on to the atmosphere. What is our atmosphere made up of? It is mostly made up of nitrogen and oxygen. Nitrogen and oxygen. Nitrogen, I think, is 71% or something like that. Or let me just quickly Google that because I never remember. Yeah, the nitrogen is 78% of the atmosphere. The oxygen is 21% of the atmosphere. That leaves about 1%, and that remaining 1% is mostly argon. And then there are trace amounts of other gases like carbon dioxide, water vapor, methane, and so on. Okay, but the atmosphere is mostly nitrogen and oxygen. Okay, so we live at the bottom of this ocean of atmosphere, and so the pressure exerted by the atmosphere on us is what we call atmospheric pressure. Okay, what is the value of the atmospheric pressure? Um, you could you could measure it by just taking. In principle, you could measure it by just taking a sheet, flat sheet, measuring its area, and then measuring the force that that sheet is feeling as a result of the atmosphere, and the pressure would simply be force divided by area. So if you do that, you would get the value of the atmospheric pressure would be approximately 101,300 newtons per square meter, or 101,300 pascals. Sometimes it's expressed in kilopascals, so in that case it would be 101.3 kilopascals. And this amount of pressure is usually called an atmosphere. That's also another unit of atmosphere, another unit of pressure, the atmosphere. Okay. Another unit of pressure that you might be familiar with is psi. So that's pounds per square inch. Uh, you know that pressure is simply weight force divided by area. So if you measure force in pounds, and if you measure area in square inches, then you can get a new unit of pressure. It's pounds per square inch. That's called psi. So in psi, that's about 15. The atmospheric pressure is about 15 pounds per square inch. Right? Okay. Is this a large pressure? Just imagine that I have uh, a sheet of paper which is 10 inches wide, a square sheet of paper which is 10 inches wide and 10 inches thick. So 10 inches long, 10 inches wide. So what is the area of this? So it's going to be 100 square inches. What is the atmospheric pressure on one side of this sheet? So it's the atmospheric pressure is 15 pounds per square inch. So the force exerted by the atmosphere on this sheet of paper is going to be 15 pounds per square inch multiplied by 100 square inch, which is going to be 1500 pounds. So if you just imagine holding a sheet of paper which is 10 inches long by 10 inches wide, on one side of that sheet you have 1500 pounds of pressure, of force acting as a result of the atmosphere. So how are you able to move that sheet? Why is it not pinned to the ground all the time? The answer is the 1500 pounds of force we just calculated is acting down on the sheet because we're using this area, but it's also acting from the other side. You have the same 1500 pounds of force acting from the other side. And since you have the same force acting from both directions, the net force on this is zero, and so we don't notice it. Okay, so that is what I meant when I said that we don't ever notice the atmospheric pressure just because the atmospheric pressure is everywhere around us, right? So it's only when the pressure becomes different from atmospheric that we begin to notice it. One rather amazing example of that is the following. There was once an incident where one of these oil tankers it's a train whose with cylindrical compartments like this, which transport oil or other fluids. So a cleaning crew came in one night and they steam cleaned the inside of the apartment, and then they closed it. And remember that since this transports fluids, it's absolutely watertight. So they, after steam cleaning the apartment, the compartment, they shut the hatch and airtight hatch and left. And what happened the next day was this. This is what it looked like. Now, this is not the actual incident where this happened. This is a video recreation of it where they do the exact same thing, and I'll let you watch that video. You can probably watch it better on your own computer. So what they did here was they filled this with steam and then just shut it and let it cool. And you can see how it implodes. So why does it implode like that? When it was being steam cleaned, the entire compartment was filled with steam, right? So the steam displaced the air and took its place, and so most of the compartment was filled with steam. All right, then they closed the hatch, right, and left. So what happens to steam when the temperature gets cooler? It condenses to droplets of water, right? And so inside the compartment, all the space that was being taken up by the steam has disappeared and now is transformed into droplets of water. So there's a lot less gas inside than there was before, right? And so the pressure inside is lower than atmospheric. The pressure outside is atmospheric. So what happens is that there is a pressure difference between the inside and the outside, right? And if you multiply that pressure difference by the area of the compartment, then you get the force, right? And the compartment is pretty large, so the area is large. Uh, the pressure difference can be, the pressure inside would be very small, right? So the pressure difference would almost be, it would be P atmospheric minus some very small quantity. So approximately P atmospheric multiplied by area. I'm using an approximate symbol here. And so the area is large. The P atmospheric is pretty large, 15 pounds per square inch. So that would be an enormous amount of force acting on the compartment. So this is the net force acting on the compartment. There would be an enormous amount of force acting on the compartment, and that is what crushes it. So hopefully that's clear. Okay, now the next thing that we're going to talk about is how do you measure atmospheric pressure. So a device which measures atmospheric pressure is called a barometer, and barometers have been in use for a very, very long time, since the mid 1700s. The first barometer was invented by Torricelli, and the way it works is the following. Okay, so let me move the diagram over here. So so to understand a barometer, just imagine that you have a tube which you fill with mercury, like here. And once the tube is completely full, there's no air bubbles or anything, you plug the tube, invert it, and put it in a pan of mercury, right? So you would find that some of the mercury now begins to flow out of the tube and fill up the pan, but the mercury stops flowing once its height reaches about 3/4 of a meter, like 76 centimeters. So this height is approximately 76 centimeters. This is something that surprised Torricelli when he did this experiment for the first time, because he probably expected that all the mercury would flow out. But he was surprised to find that all the mercury doesn't flow out. Once the height of the mercury column in the tube reaches around 76 centimeters, it stops flowing. Now, why does the mercury stop flowing out once its height is 76 centimeters? Let's try to understand that. So let me draw this vat of mercury over here. Let's draw this tube. And what we just said is that the mercury level will not fall further beyond, this is all mercury, 76 centimeters. So let's call this height h. I'll use a different color here. Okay, now let's try to understand why the mercury isn't flowing any further. Consider a point over here and another point over here. Okay, what can you tell me about the pressures at these 2 points? Clearly the pressures have to be the same, otherwise the liquid would flow, because liquids always tend to flow from high pressure to low pressure. So if this point is A and this point is B, I'm just writing the A and the B a little bit further away, just not to clutter the diagram. I could just write them here, A and B. So if the pressure at A and the pressure at B were different, then the fluid would continue flowing, right? But since the fluid is no longer flowing, I can say that the pressure at A is the same as the pressure at B. Since the fluid is not flowing. Okay. All right. Now, what is the pressure at B? So pressure at B is simply atmospheric. Why is that? Because B is in touch with the atmosphere, right? What is the pressure at A? The pressure at A is caused solely by the column of mercury above it. So what is there above A? So there is the column of mercury, and then there is this empty space. That doesn't exert any pressure. So the pressure at A is caused solely by the column of mercury that's sitting directly above it. We know how to calculate the pressure due to pressure at a certain depth underneath the surface of a fluid. So that is going to be pressure at the top plus H rho g, the formula that we just derived. The pressure at the top of our mercury column is 0 because there is empty space above it, right? So it's just going to be H times rho mercury times G. So you get this equation for this arrangement, and you can see that the height of the mercury column is a nice proxy for the atmospheric pressure because the rho hg and rho hg and g are constants. So if the atmospheric pressure fluctuates, that will be reflected in a change in H. So this arrangement that I have over here is a barometer. It's a device which will always tell me what the atmospheric pressure is. I just need to keep an eye on the height of the mercury column. And so, in fact, this is how barometers worked for a very long time. Nowadays, of course, there are more sophisticated ways of measuring pressure. But this is the principle of a mercury barometer. And here is a mercury barometer, which is just made a little bit nicer than my diagram, so you can easily read off the pressure. Okay. So you can see that, so it turns out that normal atmospheric pressure corresponds to about 76 centimeters of mercury. You can easily calculate that if you set P atmospheric to be the normal atmospheric pressure, which is 101.3 kilopascals. You can look up the density of mercury, you know what the value of G is, so you can solve for H. So you can find that for normal atmospheric pressure, H is about 76 centimeters. And that inspires a new unit of mercury. We've seen plenty of units of new unit of pressure. We've seen plenty of units of pressure so far. It's the cmHg. cmHg is just a unit of pressure, which basically all it means is that the pressure exerted by 1 centimeter of mercury. And 76 cmHg would correspond to 1 atmosphere. Right? And similarly, you can have another unit of pressure, which is the mmHg, which is the pressure exerted by 1 millimeter of atmosphere, 1 millimeter of mercury. And that the mmHg and the cmHg are small units of pressure, so they are more convenient for measuring smaller pressures. You are all familiar with mmHg. Can you think about where you've seen mmHg? Well, if you measure your blood pressure, normal blood pressure you might be familiar with is 120 over 80. Where does that, what units are those numbers in? The answer is in mmHg. Okay. Hopefully it's clear to you how to convert cmHg into pascals. So cmHg just means the pressure of a column of mercury which is 1 centimeter high. So you would just use this formula H rho g. You would put H equals 1 cm. Rho is the density of mercury, and G, you know, is what, 9.8, and that would give you 1 cmHg in pascals. Okay. I have a problem based on mmHg in the next slide, which you can take a look at on your own.